Hello, welcome to this lesson of the Linear Algebra Tutor. What I want to do in this lesson is begin the discussion of eigenvectors and eigenvalues, and I want to give you a little motivation. What usually happens in linear algebra class is you spend a ton of time talking about everything we've learned, determinants, inverses, row reduction operations, homogeneous systems of equations, and all of the things that we've done. And then you get to linear independence, which we've talked about quite a bit. And basically we get down to the point where you get down to the point where eigenvectors and eigenvalues are covered, and they just dump you right into the chapter on eigenvectors and eigenvalues. And you don't really have a good idea why it's really useful. It's not too hard to mathematically figure out what they are, but it is, I think, worth taking a second to understand at least one example of what they might be useful for. First thing is, I will say, eigenvectors and eigenvalues, they show up all the time in all branches of science and engineering. They are properties of a matrix that will just be able to be calculated. And as you know, matrices can be used to describe everything from systems of equations to rotation transformations, translation transformations. Matrices can be used to describe vectors, for instance. So there are lots of applications for matrices, and because eigenvectors and eigenvalues are properties of matrices, of course, those eigenvectors are going to pop up everywhere. But I'll give you a little bit of a motivation. Eigenvectors are extensively used in quantum mechanics when you get into more advanced physics. The different states of matter, looking at hydrogen atoms and other atoms and the various energy states, they're all describable in terms of eigenstates or eigenvectors of the system. You get into eigenvectors in control systems, electrical engineering. You use eigenvectors extensively in differential equations. If you've ever taken a differential equations course, or if you plan to, you're going to get into eigenvectors pretty, about halfway through your class. And eigenvectors are used in solving systems of differential equations. And as you know, differential equations can be used to model anything from electric circuits to control systems to anything out there. So the bottom line is since eigenvectors and values can be used to describe differential equations or used to solve differential equations, and because differential equations are everywhere in pretty much any system you study, then of course it follows that eigenvectors and values are used in every branch of engineering and science. But I do want to leave you with one specific example. It's not necessarily the most important example in the world, but it is an example that will give you a little bit of motivation as we calculate these things as to why they might be important. All right, so here is obviously a flashlight. Nothing special about it, but I need you to use your imagination. Pretend that this is a cylinder. In other words, pretend that the end of this is not flared and it's actually just a cylinder, the same radius all the way down, and we have a constant length, okay? So when you study mechanics, especially rotational mechanics, when things are rotating like this, we talk about inertia a lot. We talk about rotational inertia, and you end up figuring out and studying a matrix called the inertia matrix quite a bit when you're looking at rotational systems, okay? And a lot of times we look at this and we look at the symmetry and we try to figure out what axes are the special axes or the principal axes of rotation in a system like this. Now, since this has symmetry, one of the principal axes of rotation is right through the center of the cylinder. If you could visualize an axis that runs all the way through it, all the way and comes out the top, that is one of the principal axes of rotation of the cylinder, because I can rotate it about that axis, which means I'm basically going lengthwise and I'm rotating it. And you've got to, again, imagine this is a perfect cylinder without this flared end. The mass distribution from the axis of rotation to the edge of the cylinder is always the same. In other words, that axis runs through the end of it, and no matter where I look on that axis all the way around, as I'm rotating, I'm seeing the same amount of mass on both sides of the axis all the time. So that's a special axis. It's called a principal axis of rotation. Also, again, forget about the flared end. An axis looking like this through the center of mass this way is also a principal axis of rotation, because if I rotate about that axis, which means I'm going like this, about this axis like this, then no matter if I look from here to here or from here to here, I'm going to see the same amount of mass equivalently distributed on both sides of that axis of rotation. Also, there's another axis of rotation coming in perpendicular to the other side. Same thing, I can rotate it this way. I'm going to have the same amount of mass distributed. So for a three-dimensional object, there's always three principal axes of rotation. For a cylinder, it's pretty easy because it's symmetrical. Here's the axis, where I have nice mass distribution around that way. Here's another axis where I have mass distribution this way, and of course I have the lengthwise axial guy where I can rotate that way, and I have nice mass distribution that way. Very, very simple. But when you study mechanics and you look at this rotational inertia matrix, what you end up finding is that these principal axes of rotation end up being, here's the punchline, the eigenvectors of the inertia matrix, right? Basically, that's what they end up being. So when you learn how to deal with matrices and you learn when you learn how to calculate the eigenvectors of a matrix, if you represent the mass distribution of this object as a inertia matrix is what we call it, then the eigenvectors that you get as a result of that are going to be the principal axis of rotation. Now for this object, it's very simple because it's a cylinder and we can guess the axis of rotation. But you may have a complicated blob, or in fact, what if you took this flashlight in its actual shape, where you had, you know, a flared end, maybe like a weird thing hanging over here, then the principal axis of rotation will not be quite so obvious to you at first glance. You may not know exactly where to place them, but you can represent this object in matrix form when you take a mechanics class and you learn how to do that. And then you can find the eigenvectors, which will correspond to the principal axis of rotation. So it's just a simple example. I'm not going to write anything on the board and show you how to do any of that. It's just a motivation. Eigenvectors and eigenvalues, they pop up all the time in science and engineering, and they are, you know, very useful, and this is just simply one idea and one example that I think everyone can wrap their brain around and say, oh, okay, I can see how this axis of rotation business could be useful for three-dimensional objects. But the truth is, you end up using eigenvectors all the time in different branches of science and engineering, so keep that in mind. What we're going to do in the next section is we're going to introduce the concept of the eigenvalue problem, show you how to calculate these eigenvalues and what their corresponding eigenvectors are. Just remember, eigenvectors, eigenvalues, they go together like peanut butter and jelly. You really can't talk about one without talking about the other. So follow me on to the next section, and we'll start the journey with eigenvectors and eigenvalues.